All right. Thanks for coming. So today we have Dr. Yulai Ma from Paderborn University in Germany. Yeah. Here's another pseudo German. Right. We will talk about we will talk about perfect matchings. Yeah, please.
Yeah, thank you for the introduction. Today I want to talk about perfect matching in regular graphs. This is a widely studied area in graph theory. And our focus is on the pairwise disjoint perfect matchings in the regular graphs. This talk is based on the joint work with David Modiolo, Eka Stefan, and Isaac Wolf. So before giving the program, I want to go over some basic definitions. Here we always consider the graph, which may have some parallel edges but no loops. And according to the weighting theorem, we know simple regular graph can be divided into two classes, class 1 and class 2. So here, and our regular graph is said to be class 1 if it has R pairwise disjoint perfect matchings, otherwise it's class 2. And this definition can also be applied for the multi-graphs. For example, we consider three regular graphs here with some parallel edges. And it's easy to check this graph has three pairwise disjoint perfect matchings, so it's class 1. So with this definition, we know any R graph. So for the general R graph, it seems this necessary condition is not enough to guarantee the graph to be the class 1. But if we limit it to the planar case, it's true, or at least for the cubic case. Here, in 1880, Ted proved equivalence of the four-card theorem. It states every Bridges planar 3 regular graph is class 1. It means it has 3 pairwise disjoint perfect matchings. And for to simplify the discussion, we defined the regular graph with this condition as a special graph called it R graph. So now we can restate this statement as follows: every planar 3 graph is class 1. And actually, Simon thinks this statement can be generalized to high degree regular graphs. So he conjectured for any R, every planar R graph is class 1. And this conjecture has been verified for some small values. For R equal to 3 is equivalent to 4-card theorem. For R equal to 4 and 5, Greening proved it using 4-card theorem. But his results are not published. So last year, Nazaros and Yu gave a new proof of this case within the decomposition of signed graphs. And for the R equal to 6, 7, and 8 are also verified by different groups. But it's still open for the case R is at least 9. And this conjecture is also verified for some subcase of planar graphs. It's like K4 minus 3 graph, and K5 minus 1 edge minus 3, and K3 minus 3 graph. It's very close to planar graphs. And surprising, actually, this Simon in that conjecture will also hold for some non-planar cases. In this paper, in the paper about R equal to 6, the authors mentioned Simon has a stronger conjecture. It's about Pearson minus 3 graphs. So he conjectured actually for R is at least 1, every Pearson minus 3 graph, R graph is class 1. And for this conjecture, there are not too much results. But for the case R equal to 3, it's equivalent to the well-known TAT3 edge carrying conjecture, I would say. And its solution has announced, they announced it's proved, but I think one paper is not published about the apex graph. And so now we have two conjectures. one is about Penny case, and the other is about Pearson manifold case. So we want to prove the equivalence of them. Then we can have some results. And recently we did a small step in this direction. We can prove simple exact conjecture is equivalent to the statement that every K5 manifold graph is class 1, and also equivalent to the statement every K33 manifold graph is class 1.
Sorry, maybe I missed the definition. What does the definition of R graph? I mean, as I remember, it's R regular.
Yeah, it's a special R regular graph.
Yeah,
But it satisfies the condition for any vertex set with odd size. It connects to its complement at least R edges.
But as I remember, in previous slide, there's a 6 or 7 planar regular graph. Then what does it mean? Planar 6 graph.
Oh, it's
It's a multi-graph.
you can have a parallel edges.
I see. Thank you.
Okay, so we have this theorem, but you see there's still big gap to bridge, right? From the K5 manifold to the Pearson manifold graph. But I think it's a bit hard to deal with it. Because for the K5 manifold graph, we have the characterization from Wagner, but for other graph, we don't have this good characterization, so we don't know how to deal with it. Yeah, the above conjecture and the results is about Pearson manifold graph, so we want to know what happens if we consider the graph with a Pearson minor. Does this simple exact conjecture still true? Obviously it's not, because Pearson graph has is class 2, and actually for any R, we can construct a R regular graph of class 2, and the way is to add perfect matching into the Pearson graph. Yeah, as I said, for Pearson graph, if we add a perfect matching into it, then it's still class 2. So now we add R-3 perfect matches into the Pearson graph, then it's still class 2. And then now it's R graphs. Yeah. So now we know for the parent case, maybe it's class 1, but for the general case, it can be class 2. So we are curious how many pairwise disjoint perfect matchings can be found in these class 2 graphs. And we observe some results. The first one is every R graph has a perfect matching. That means it has at least a 1. Then we want to improve it. If every R graph has at least 2, that's wrong. But Pearson graph only has 1. We cannot find the two disjoint perfect matchings in a Pearson graph. But every two perfect matchings in Pearson graph intersect. And actually in 1999, Guzzi has proved for any R, we can always find an R graph in which every two perfect matching intersect. So that means we can do nothing. But then we find in all of these R graphs, they have a property that with this property has a 4H card. So then another question is, if we consider the graph in a very high H connectivity, then can we guarantee there are more pairwise disjoint perfect matches? To study it, we define that these parameters is the maximal number of pairwise disjoint perfect matches, which can be found in all R graphs with the H connectivity lambda. And for these parameters, we see they have two parameters, lambda and R. So for the first case, is R equal to lambda. Lambda equal to R. Then in 2020, Thomason gave a question: is MRR at least R minus 2? It says every RH connected RH connected R graph has at least R minus 2 pairwise disjoint perfect matches. Yeah, it's trivial for I equal to 2 and 3. But to 2, the lower bound is 0, and when I2 is equal to 3, then the row bound is 1 because every R graph has at least one perfect matches. So it's trivial. But for 4, there's already some counterexamples from Erzi and Mazzucchello. So in 2021, Maggioro and Stefan give some construct some. I want to show our constructions. So our constructions is from the Pearson graph. Yeah, actually, I think the Pearson graph has some good properties in our constructions. So we start with the Pearson graph and add R-2, R-3 perfect matchings into the Pearson graph to get R graphs, such that the resulting graph contains a multi-edge which contains of R over 2 edges. It's like if you think of this multi-edge from this vertex to this vertex, and this multi-edge consists of R over 2 edges, parallel edges, then the left part is the graph what we want at the first step. And then we remove the multi-edge from this vertex to this vertex and take a copy on the right side and then glue them at this specific vertex. Then this graph is almost regular, except this vertex and this vertex. But we won't get a regular graph. So we add n over 2 pending edges here and also here. So now this gives us a graph, a regular graph QR. And we find this QR has some good properties with this lemma. Let G be a graph with R-2 pairwise disjoint perfect matches, and QR is an induced subgraph. Then half of this R-2 pairwise disjoint perfect matches include edges from E1, and another half include edges from E2. Then we use QR in our construction. This is QR. The construction is the last slide. So now for the case model 4 is 0, we give construct these structures. We can prove if a regular graph contains this structure as an induced graph, then this graph cannot have R-2 pairwise disjoint perfect matches. It's because we can prove it by way of contradiction. Suppose this graph is a R graph and has R-2 pairwise disjoint perfect matches. Then we calculate the intersection of this edge card around these three vertices, the edge set around these three vertices, the intersection of this edge card and M. M is the edges of all perfect matchings. What does it mean? It says because every perfect matching contains exactly odd number edges from C. C is the set of these three vertices to the remaining set. So for M, for this pairwise disjoint perfect matchings, we will have even number of we use this double counting techniques. We count it first with this perfect matching, the definition of the perfect matchings, because it's R graph, so every perfect matching will contain all the number of edges between this card in this card, and we have R-2 pairwise disjoint perfect matching, so it means the intersection is even. And for in other direction we use QR. In last lemma, we see in QR for R minus 2 pairwise disjoint perfect matches, we always have half R minus 2 over 2 edges from E1, and there are 3 E1. So it means it's 3 times R over minus 2 over 2. Then it's odd. So with these two counting, we find a contradiction. Yeah. Then you see here is the each connected graph without fixed, and this part is R. This part is R. And for a second, from the vertices construction, we know there is a each connected R graph in which every two perfect matching intersect. So that means 4R is 1, and from the construction for the Pearson graph, by adding some perfect matchings, we know there are some R graph of class 2. So RR is at most R minus 2, and this upper bound is improved to R minus 3 for even R by R1 constructions. And also, if you reduce the edge connected to R minus 1, then there's a upper bound for R minus 2, R minus 3 as well. As you see, actually, we don't have too much result here, right? Because if it's class 1, then it's it means every R graph has R pairwise disjoint perfect matchings. Otherwise, it has at most R minus 2. And now the upper bound is always R minus 2 or R minus 3. We cannot go further. Then we give a general upper bound. We can prove for any even lambda, one is at least 6, and every R, which is bigger than lambda, then there's lambda H connected R graph without 3 lambda over 2 minus 5 pairwise disjoint perfect matchings. That means the upper bound of M lambda R is 3 times lambda over 2 minus 6, which is independent from R. And you may find that we have a limitation for this lambda is even. That's because for R graph, the H connectivity is even or equal to R. Because we had already limitation do the limitation for the order sized vertex set, so we just force on the even sized vertex set. That's why the H connectivity is always even or equal to R. And we have in the last result we have already considered about lambda the case lambda equal to R. So now here we consider the first case when the H connectivity is even. Yeah, and this proof is a bit complicated. So here I just use the case lambda equal to 8 to show our idea. And now the theorem for this theorem is like for every R, there is an 8 edge connected R graph without 7 pairwise disjoint perfect matchings. And this proof is proved by induction on R. At first, we find a 8 edge connected 8 graph without 7 pairwise disjoint perfect matchings. It's possible because we had already proved M6 is at most 6. Then what we want to do is add some edges into this graph, such that the resulting graph is still 8 edge connected, and the degree of every vertex is bigger, and it cannot have 7 pairwise disjoint perfect matchings. So the way is, first we find a perfect matching in G8, such that every edge is in a multi-edge consisting of some parallel edges. Actually here we want to find a perfect matching such as every surprising operation. We delete these two multi-edges and glue them at these two specific vertices. And then we can prove after this surprising operation, the graph is still R graph. It's still nine graph, and the edge connectivity of this graph is still 8. And this graph has 7 pairwise disjoint perfect matches. So now we have this graph. It's edge connected 9 graph with 7 pairwise disjoint perfect matches. Then we go back. We can prove in this 7 pairwise disjoint perfect matching, it will just use 7 edges in this part and 7 edges in this part. Which means when we go back here, these two, because every perfect matching will use 1 edge here and 1 edge here. So it means there are only 3 perfect matchings using the edges here and use edges here. So it can be transformed a perfect matching in G8 with these 3 edges without green one. That means G8 plus M minus this green one edge has 7 pairwise disjoint perfect matches. Now we just do the operation for these green edges. If we do this operation for all green edges, then it means G8 plus M minus all green edges has 7 pairwise disjoint perfect matches, and the green and all green edges actually is the perfect match M. Right, that means G8 has 7 pairwise disjoint perfect matches. It's a contradiction. Yeah, but for the general case, it's more complicated. Yeah, with these conjunctions. So now we have some questions. Actually, we really want to know the exact values for m lambda r, but it seems too difficult, so we want to just improve the upper bound for it first. Also, we want to give a lower bound. For me, I think the upper bound is improve the upper bound is easier, because we just need to construct some graphs or find some counterexamples. But for the lower bound, you have to prove all RH connected R graph has at least k pairwise disjoint perfect matchings. Yeah, and it's even open for 2, so it's a bit different. And actually, in 2020, Thomas also has a conjecture. Says if for the sufficiently large R, MRR has the lower bound 2. Yeah. But it's still open now. So for the final part, I want to introduce this 5H connected 5 graphs. Yeah, as I mentioned, when we want to find a R graph of class 2, the method is add some perfect matchings into the Pearson graphs. But we see it's not the method to construct 5H connected 5 graphs. Because in Pearson graphs, every perfect matching insets. That means when you add 2 perfect matchings into the Pearson graph, then you will induce a multi-edge with 3 pair edges. And because it's 5 regular, so they are around this multi-edge, there are only 4 edges. So it means it's a 4-edge card. So we cannot use this method to construct a 5H connected 5 graph. So that means for MRR, we know nothing. It just lies between 1 and 5. We know nothing about it. So we have this program. Is it a 5H candidate phi graph of class 1 of class 2? And the reason why we want to determine this value is because it connects to some famous conjectures on 3 regular graphs. Let me introduce this graph first. So Burge-Ferguson conjecture states every 3 graph has 6 perfect matchings such that each edge is in exactly 2 of them. And the phi-respond conjecture states every 3 graph has 3 perfect matchings such that no edges is in all of them. And the 5-cycle double cover conjecture states every 3 graph contains 5 cycles such that each edge is in exactly 2 of them. Here, the cycles means a graph where every vertex has even degree. Actually, it's even graph. Yeah. So we can prove if M55 is at least 2, then phi-respond conjecture holds. And if M55 is equal to 5, then both 5-cycle double cover conjecture and the Burge-Ferguson conjecture hold. Yeah, so it seems it's a bit hard to determine the MRR. Yeah. Now here I can give a proof from the for this statement. If M55 is equal to 5, then every 3 graph contains 5 cycles, such that each edge is contained in exactly 2 of them. We can suppose G is the smallest counterexample and it's easy to check. G is 3H connected. And then for each edge in G, we double every edge to get a graph 2G. Now in 2G, every vertex has degree 6. And now for every vertex in 2G, we replace it by this conjunction. You can see now that every vertex has degree 5. So actually you can prove this graph H is 5 H connected phi graphs. Then we use this condition because if every 5H connected phi graph has 5 pairwise disjoint perfect matchings, that means the H has 5 perfect matchings. Has 5 pairwise disjoint perfect matchings.
Here, the cycle means disjoint union of
Yes, the union of
circuits.
really circuits. Yes.
Okay, so it's 2 regular.
Yes.
Right.
No, it's not too regular.
Oh, it's just a.
Yeah,
disjoint
every vertex
union,
has
so
even degree.
You call circuit as a single cycle.
Yes.
And cycle is union of circuits.
Yes.
Sorry. Okay.
Yeah. Yeah. So now we have we proved. Okay, no. If H has 5 pairwise disjoint perfect matchings, we may know every perfect matching will connect two edges from this part to the remaining part. It's because this part has even order. That means these 6 edges are contained in 3 pairwise disjoint perfect matchings. So now when we go back to G2, these 6 edges will induce 3 cycles. Okay, I should say it in this way. So 3 cycles will contain the vertex here. That means these 5 pairwise disjoint perfect matchings of H will transform into 5 cycles of 2G. actually is edge decomposition. And then when we go back to G, it's a 5 cycle such that each edge is contained in exactly 2 of them. Right, because every edge is doubled here, and for 2G we have the 5 cycle decompositions of 2G. So when we go back to G, every edge is contained in exactly 2 of them. So then we're done. Yeah, that's all.
Thank you. Any questions?
So so you say you don't have any lower bound users. So for specific R, something like zero modular for, then do we know the lower bound in this case? I mean, what MRR?
We don't know.
Do you believe that this is linear on R or?
It's hard to say actually. Yeah, because for 4, it's just 1, right? So, and for 5,